All right, here's our second video. In this case, we're going to be talking about what happens when a weak acid is mixed with a strong base, and we'll see what results. So here's our summary. When a weak acid and a strong base are mixed, they react quantitatively in a reaction represented by the following. HA plus OH minus forms A minus plus H2O. So we're going to look at 6 different points in this process, and you can see they're numbered there, 1 through 6. This is likely going to take more than one video, but each video is no longer than 15 minutes. So I don't want to be rushed. This is going to require some thinking and some calculations. So we'll get right to it here. So in the first case, we're going to look, before we add any base, what's the pH of this of this weak acid. So we have nitrous acid, HNO2. You recall HNO3 is a strong acid, but HNO2 is not. It's a weak acid. So it ionizes in an aqueous solution according to this equation. HNO2 plus water forms, or it comes to an equilibrium with H3O plus and NO2 minus. Ka is given as 4 times 10 to the minus fourth, not an especially small Ka. So we want to calculate the pH of a 0.2 molar solution of HNO2. All right, so when we do this, we set up our rice box. We have 0.2 moles per liter of HNO2, none of H3O and NO2 minus. And of course, we don't concern ourselves with the water concentration. We know that this is an equilibrium reaction, so we do minus X because we don't really know how much HNO2 disassociates to form H3O plus and NO2 minus, but we know that stoichiometry tells us it's a 1-to-1 ratio. So we write minus X for HNO2 and plus X for H3O plus and NO2 minus. So our equilibrium position is 0.2 minus X for HNO2 and X for H3O plus and NO2 minus. Now, we write our equilibrium expression. Pretty straightforward. At this point, we've done this a few dozen times. So we get this reaction. We get 4 times 10 to the minus fourth is equal to the concentration of H3O plus times NO2 minus divided by HNO2. So when we plug in what we know and what we don't know, we get X squared divided by 0.20 minus X. Now, I don't really think that Ka is small enough to be able to make this simplifying assumption. So we're going to have to solve the quadratic. When we do that, we get X, which is equal to H3O plus, is 0.00875, and therefore pH, being the negative logarithm of that number, comes out to be 2.06. Definitely acidic, what we expected for a not very dilute solution of HNO2. But had we made the simplifying assumption, we would have solved X and we would have gotten 0.008944, which, that's not very different from what the actual value is, but we made an assumption without a solid basis for doing that, and that's going to get you in trouble. So we want to avoid doing that when we want to avoid making assumptions that we can't back up with fact. This is one where we cannot, so we don't. And we get 2.06 for the pH. All right, moving on to step 2, or step B. We add some base, and now we are before what we are going to call the half equivalence point. I'll explain that in just a minute after we get past this point. So here we've got 0.2 molar HNO2, 50 milliliters of it. And we add to that 0.2 molar sodium hydroxide, a strong base, 20 milliliters of it. Okay. Now, we can see that if we add these two volumes together, we get 70 milliliters or 0.07 liters. We know that molarity is equal to moles divided by liters. Therefore, moles would be equal to molarity times liters. So knowing that, we can plug in these numbers. 0.2 molar times 0.050 liters would give us 0.010 moles of HNO2. We do the same math for sodium hydroxide. We get 0.004 moles of OH minus. And of course, we don't have any NO2 yet, NO2 minus yet. All right, now we can look at this and see, hey, there's a whole lot more moles of acid than there are moles of base. So from a limiting reagent point of view, it's pretty clear that OH minus is my limiting reagent. And therefore, all of it gets consumed in this reaction. And so that is, we write minus 0.004 for HNO2 for OH minus, and positive 0.004 for NO2 minus. And we get to equilibrium, we see that we have no moles of OH minus and 0.006 moles of HNO2 and 0.004 moles of NO2. Now, we can compute the concentration because we now know the total volume is 0.07 liters. So if we take my 0.006 moles divided by 0.07 liters, I get 0.086 molar HNO2. And I do the same for my NO2 minus, I get 0.057 molar. Now, why did I do this? Well, because of my reaction, which is on the R row of my rice bowl, I can see that Ka, which is still 4 times 10 to the minus fourth, that's now equal to H3O plus NO2 minus divided by HNO2. Now I know NO2 minus because I just calculated it, and I know HNO2 because I just calculated it. The thing I don't know is H3O plus. Okay, so because this is still in equilibrium, this relationship holds, and I can now solve for H3O plus. And when I do that, I get 6.04 times 10 to the minus fourth, okay? And I can do my pH calculation, the negative logarithm of that number, and I get 3.22. Let's think about this for a minute. We started out with acid and no base. We added some base. We would expect the pH to come up, and it does. So now my pH has come up to 3.22. All right, now the next step, we're going to get to what is called the half equivalence point. All right, so here I still have my original 50 milliliters of acid, and now I've added 25 milliliters of sodium hydroxide. And when I add these two volumes together, I get 75 milliliters, 0.075 liters. And I see that, I've got that same concentration or that same number of moles of HNO2, which is 0.05 liters times 0.2 moles per liter, get 0.01 moles of HNO2. And I can do the same mathematical exercise for sodium hydroxide when I multiply the molarity times the volume, and I get 0.005 moles. Now, we can see that, again, the OH minus is the limiting reagent, and it gets completely used up. But the reason we call this the half equivalence point is because I've used up exactly half of my excess reagent, whether it be base or acid. I'm halfway there. So now when I do this arithmetic, I get 0.005 moles of HNO2, no OH minus as before, and 0.005 moles of NO2 minus. And when I divide by the volume, which is 0.075 liters, I get 0.0667 for both items, both reagents, HNO2 and NO2 minus. So now, when I write my Ka expression, I have the same numerical value in the numerator as I do in the denominator, which means they both cancel. And I'm left with H3O plus is just the same value as the Ka. And so when I take the pH of this, I end up taking the negative logarithm of 4 times 10 to the minus 4th, or now 3.40. So the pH continues to rise. Exactly what we expect, because we continue to add more base to the same amount of acid. So we would expect our pH to continue to rise. Now, at this half equivalence point, two things are true. The definition of the half equivalence point is when half of the acid, or it could be base if we're doing it the other way around, when half of the acid is consumed, then we know that pH is equal to pKa. Really, the p function, remember, is just nothing more than the negative logarithm of some number. So pH is equal to pKa at the half equivalence point. All right, now let's move on to the next step. I get past the half equivalence point. I add just a little more base. I've gone from 20 to 25 to now 30 milliliters. The total volume is now 80 milliliters. And I do the same math once more. I multiply my volume in liters times my molarity to get the number of moles. And I can see that now I have 0.006 moles of OH minus. I subtract that from both HNO2 and OH minus, and of course I'm going to get 0 moles of OH minus just as before. But now I don't have a whole lot of acid left, 0.004 moles and 0.006 moles of NO2. I could divide by that volume to get the concentrations, and I get 0.05 molar and 0.075 molar. I write my Ka expression, and now I have these numbers. I solve for H3O plus, 2.66 times 10 to the minus 4th. I take my negative logarithm. I get 3.57. No surprises here. We're just watching the pH tick higher and higher. Still acidic, still not a big swing in pH. But we're going to stop this video right here because we are at a good stopping point, and we'll pick up again in the next part and watch what happens to the pH as we continue to add more base.